Hey guys, this is Mr. Shower's video on empirical formulas. Now, as a whole, empirical formulas is actually very simple, but there's a few important steps that you must go through in order to do it. So I'm going to show you guys some basics, then we're going to go over a couple examples, and you really have to take the time and go through it to understand what's going on. So we're going to look at some language and then go through with how to calculate them. Now, percent composition is a good thing to understand. If you don't understand what percent composition is, I would go back and watch a video on percent composition before you start this, because it's pretty much how this empirical formula calculation goes. All right, so let's get started without further ado. Okay, so what is an empirical formula? An empirical formula consists of the symbols for the elements combined in a compound with subscripts showing the smallest or reduced whole number ratio of the different atoms in the compound. Okay, now what I like to say is the empirical formula is the lowest or more reduced formula. So we have this example right here, C4H2O2. You can reduce this all the way down, divide each one of these by 2, and you get C2H1O1. Now, this is the empirical formula of this formula here. Now, empirical formula C2H1O1 may have additional molecular formulas. So this might not be the only formula that can be reduced down to this one. There could be others as well. Okay? So note, an empirical formula may have many molecular formulas, ones that are greater in numbers. Okay, so here we go. Here's an empirical formula, CH. CH can have 2 additional molecular formulas, like one, acetylene, which is used in cutting thick pieces of metal, and styrene. Okay, they both, if you reduce acetylene, divide each one of these by 2, you'll get CH. If you divide both of these by 8, you'll both get CH. Okay, so that is the empirical formula. All right, just to give you a basic example. Now, how do we determine the empirical formula of a compound? It's actually quite simple. So a compound is analyzed and found to contain 25.9% nitrogen and 74.1% oxygen. So here we have 2 elements and the percent. So this is the percent composition of this compound. Okay, so our question is, what is the empirical formula? Okay, so our empirical formula is going to be N question mark, O question mark. We don't know these, but we do know this. We do know the percent composition. Okay, so the first step is convert percent to grams. So just simply switch percent to G. Okay, we always assume we have 100% of the compound. Therefore, we take the percent given and convert it to a decimal, which is basically going to be in grams. Okay, so here we go. So we have 25.9% nitrogen, which we just convert to 25.9 grams nitrogen, and the same thing for oxygen, 74.1% O, which equals 74.1 grams O. And remember, percent means parts per 100. So both masses must add up to 100 grams, which they do. Take a calculator and add these up. They equal 100. Okay. Conversion factor time. We have to figure out which conversion factor we're going to use. Now, every conversion factor has 2 options. One for going one way, one for going the other way. Okay, so you have 2 options here, 1 choice. Now, the one you're going to want to use is this one right here, where 1 mole is over mass. That way we can get mass to cancel out, and we're going to be given the answer in moles. Okay, so step 2, convert each atom's mass in grams to moles. Okay, so we set each one up like this. Okay, here's the conversion factor we're going to use. Now, the molar mass for nitrogen goes here. We simply just put the number that's associated on the periodic table for the mass of nitrogen, which is 14, there. Okay, and we put 16, which is found off the periodic table, here for oxygen. Now, our grams can cancel out for both of these equations, like so, exposing moles in the numerator. Okay, and we get our answer, 1.85 mole N and 4.63 mole O. Now, the mole ratio of N to O is simply 1.85 N and 4.63 O. Now, this is kind of an interesting point here. Now, we can't have a fraction of an element, right? There's no way. It just doesn't work. We can't cut one element partially down. So what we have to do is we have to go on to another step, and we have to simply divide each one of these numbers by the lowest mole number that we get. So let's check out step 3. Smallest whole number mole ratio of atoms. Okay, so divide each molar quantity that we just found in step 2 by the smaller number of moles to get 1 mole for the element with a smaller number of moles. This will give you the empirical formula. Okay. Now, if both are not whole numbers, proceed to the next step. So we should be getting a whole number. If not, that's okay. We'll have a step 4. So in this case, we take the 1.85, which is the lower of the 2 moles, divided. So therefore, we get 1 mole N. Perfect. We get a whole number for at least the 1. But then this one over here, we only get a 2.5. Okay, so now our ratio is 1 to 2.5. Not good enough. So step 4 is where we have to fix this problem. Okay, and it's the last one. It's pretty simple. So what we want to do is we want to round to the nearest whole number. So we want to multiply each part of the ratio by the smallest whole number that will convert both subscripts to whole numbers. Now, you want to start with a 2 and work your way up 3, 4, 5, if you have to. I've never gone that high. Usually like 2 or 3 is basically it. Now, we want to get a whole number. So in this case, 2 worked out for us. So I put a 2 here. So 1 times 2 is 2. 2.5 times 2 is 5. So there we go. We have our whole numbers now. So our ratio is 2 to 5. So N2O5. That is the correct empirical formula. Okay? That's the most reduced form that we can get. So it's an important step, both step 3 and 4. But this is how we go about getting our empirical formula. Now, empirical formulas aren't supposed to be tricky. It's just a formula that we need, that we do in lab work to help us get something called the molecular formula, which we'll look at later. Okay, let's look at a couple basic examples. Okay, so there's 3 of them. Very similar to what we did. Okay, here we go. Example 1. The percent composition of diborane, okay, contains 78.1% B, or boron, and 21.9% H, or hydrogen. What is the empirical formula? Now, boron's mass in the periodic table is 10.8. Remember to round it to 11. Do not forget to round your mass numbers on the periodic table. Okay, so like we did before, we want to convert the mass in grams to moles after we convert the percent to grams. So this was 78.1% grams. Now we go to moles. So here's our conversion factor. Off the periodic table, we have 11 grams boron. The grams cancel out, giving us moles. And then for hydrogen, we have 21.9 grams hydrogen. Divided by 1.01, we get 21.7. Now, we want to find the ratio here. Okay, so we want to divide each one of those by the lowest mole number, which is 7.10. Okay, so we divide both of the numbers found by 7.10. And it turns out that we get 1 for B and 3.05 mole of H. Now, this is very, very low. This is very close to 3. So we can just say it's 3. Okay, so it's a 1 to 3 ratio. Perfect, we're done. We do not have to go further. Okay, this is like step 3, and we finished step 3 from the first example I showed you. Okay, we do not need to go on step 4 in this example. All right, let's look at another example here. Okay, qualitative analysis shows that a compound contains 32.8% sodium 22.65% sulfur, and 44.99% oxygen. Find the empirical formula of this compound. Okay, so we want to go grams to moles. All right. Okay, so we're given percents. Just convert these to G's, and we go to moles. Okay, so here we go. Here's our grams. Okay, our molar masses are 23 grams for sodium, 32 grams for sulfur, and 16 grams for oxygen. Okay, divide each one of these, and we get these moles here. And we divide each one of these three by the lowest, by 0.7, each one of these. Okay, in this case, we have 1.4 divided by 0.7, 0.7 divided by 0.7, and 2.8 divided by 0.7. And look at this, 1.9, 1, and 3.9. These all work out. So this actually is very close to 2. This is 1, and this is 4. So here's our formula, Na2S1O4. Simple. Okay. Now, the last example is analysis of a 10.15 gram sample of a compound known to contain only phosphorus and oxygen. Indicates phosphorus content of 4.433 grams. Now, to calculate phosphorus, it's very simple. We would subtract these two numbers, and you would get phosphorus. Okay. Now, what is the empirical formula of the compound? Okay. Well, first off, we have our phosphorus is 4.433, and our mass of oxygen is 5.717. All right. So then we have grams of phosphorus and grams of oxygen. This should be an O. Okay, this is O. All right. Now, that's an O. We end up getting our 0.1431 mole of phosphorus and our 0.3573 mole of O. So now this one here is a smaller amount, so we're going to divide this number by both of them. Okay, oops. So 0.1431 mole P divided by 0.1431 and 0.3573 mole O divided by 0.1431. So we get 1 to 2.5. Okay, now we're at the place where we need to go to that next step. So in this case, we have 1 mole P, but we have 2.5 mole O. We've seen this one before. Okay, so we can multiply both of these by a 2, which makes it 2 and 5. Okay, so now we have 1 and 2.5 times 2, so we get 2 and 5. So our formula is going to be P2O5. Okay, for our empirical formula, or least reduced formula. You can't say 1, 2.5, because remember, you can't have a fraction or a decimal for an atom. You can't have an atom cut in half. Okay, guys, that's empirical formulas. That's all it is. And remember, empirical formulas is based on percent composition, which will then be used, again, to find the molecular formula on the next step.